Okay. So hopefully should work. Station is on, and this is our first slide for today. Now, as I said at the beginning, we are focusing this part on geotechnical works, mainly on foundations. So far we have discussed, we have introduced shallow foundations, we have seen how to deal with bearing capacity and settlement of shallow foundations, and as I said, this will be all further developed during the exercises. Now today we will talk about pile foundations, foundations on piles, which means deep foundations. So let's try to get familiar with this type of foundations and what are the peculiarities of this type of foundation. Let me see. Yeah, apparently the camera is fine. Okay. Now, this specific topic can be also found in your textbook, which the textbook you have as a reference of this course. But there is a specific textbook that we would recommend to you, where you can find most of the figures and further details, and of course not all the book should be studied for the exam, because the full book is on many aspects of foundations, but can be a good reference for your also professional activity, as well as for the following courses on foundations, like the one I mentioned at the beginning, design of foundations and retaining structures, that you can you can attend next year in your second year. Now, this reference book is called Piles and Pile Foundations. It's a relatively recent textbook. The first edition was in 2012, but it was written by a research group from the University of Naples, an Italian group which I know rather well, and so I'm pretty sure that the textbook is an updated and interesting one. It is in English, of course. So you might add to your reference books this one as well. A pile, that is the typical, probably not the only, but the most typical deep foundation, is a slender structural member installed in the ground to transfer the loads to the soils at some significant depth below the base of the structure. Now, in the two pictures that you have here, you have two possible examples, but you will see you have many more. On the left, this is probably the foundation of a building. On your right, this is an offshore infrastructure where piles are the most typical type of foundation. But from the little description that you have, you immediately see that the aim of piles is to transfer the loads at some significant depth. We want essentially to reach depths, soils that are at a depth with better mechanical characteristics. We want to involve deeper soils, which are typically better from the mechanical point of view than shallow layers. Now, this is not the only reason. The other reason is related to the different mechanisms that can be activated with a deep foundations. And this is something that we have already discussed and introduced the first day when we illustrated the difference between a shallow and a deep foundation, and now in this slide this is further focused. So you see, a pile essentially is a slender, typically a cylindrical section, a circular section, transversal section, circular beam element installed into the soil. There is a concrete pile cap. This can be just a connection between different piles, or can be a raft connecting all piles, which can be bedded on top of your ground, or can not touch the ground. So all the capacity is provided by the piles, but still you have this the requirement of a concrete pile connecting the different piles, and then you have the loads applied from the superstructures, which as for the shallow foundations, this can be vertical, it can be horizontal, it can be overturning moment, all possible loading components applied to this structure. Now, how does this particular structure transfer the applied loads to the soil? With two mechanisms that, as I said, were already discussed. The first one is below the tip of the pile, and this is the tip of the base resistance. Of course, this pile depends on the size of the footing, but it is not as large as a shallow foundation. Still, there is can be. You have piles larger than 1 meter, can be 1,000 or even 1,500 millimeters of diameter. In that case, you have an important base, and you have an important contribution from the tip or the base resistance. Nevertheless, in this case, you have also the skin friction or the shaft resistance, which is developed along the shaft of your pile. And once again, if you have a large pile, for example, you have also a large side of the footing in contact with the soil around, and the friction actually developed along this shaft is, if not the only, typically the main mechanism by which the applied loads are transferred to the soil. This mechanism, this lateral mechanism along the shaft, is something that, if you remember, we typically neglect for shallow foundations, because the soil is a very small part of soil, and typically this is remolded, whereas this is the soil you have in situ, you have on site. Now, this soil can be disturbed or remolded depending on the installation technology. So, as you will see in a later slide, this is an important aspect that represents probably the most important peculiarity of pile behavior. Now we have to understand that these two mechanisms all together, if you add the two contributions, the base resistance and the shaft resistance, you end up with what is your pile bearing capacity. Typically, these piles, which, as I said, can be large piles, so have their own specific weight, it is something that you have to consider as well, the weight of the pile, which for shallow foundations can be neglected or can be added to the applied loads from the superstructure. In this case, the weight of the pile, it can be important, can be very important, and should not be forgotten. Now, deep foundations, if we think at the first initial distinction, are foundations where L, the embedded length, L, is much greater than the typical footing breadth, which in this case, if it is cylindrical, will be a diameter. So when L is much greater than D, let's say at least 10 times D, which is certainly a typical figure for piles, then we can talk about deep foundations, and for deep foundations we have to consider these two separate interaction mechanisms that are put together in order to get the pile bearing capacity as a whole. When do we use pile foundations? Piles are used when the soil near the surface does not have sufficient bearing capacity to support the structural loads. So this is the most obvious, the first thing that we have introduced. There is little you can do if your shallow layers are not good enough to support the applied loads. So you might first design a shallow foundations. You run your bearing capacity analysis, you realize the shallow foundation is not suitable, so you have to go deeper. And in order to go deeper, you have to use piles. But most of the time, if you remember, the shallow foundations can satisfy the bearing capacity analysis and verification, but not the serviceability limit state analysis, so the calculation of settlements. So bearing capacity is satisfied, but not settlements. So you want to reduce settlements. In this case, piles are much stiffer elements, more rigid. So they will develop, because they have this mechanism that we will try to understand later on, they develop much smaller settlements with respect to shallow foundations. So another reason to use piles, even if the bearing capacity is satisfied, is to reduce settlements. And this is an important aspect, because in recent times you can use a sort of mixed, sort of hybrid foundations, in which you consider the shallow foundations, the raft, for example, which is bedded on the ground. In this case, should be bedded on the ground surface, and that shallow foundations will satisfy the bearing capacity limit state, and then you will use piles to reduce settlements and to satisfy the serviceability limit state. So you will use as I said, what are called raft foundations, piled raft foundations, in which you have the two things combined together. But we have first to introduce what piles are as a separate foundation element, and then we will be able to understand better what I am saying, what I have just anticipated to you right now. When we talk about settlements, we have to be especially careful with respect to differential settlements. And once again, if you reduce settlements, you can reduce also differential settlements. And this is another reason to use deep foundations. Now, if you have important lateral loads, of course, when we studied shallow foundations, we considered also possible inclination of the resultant, possible horizontal component. We have introduced interaction diagrams, but of course the capacity under horizontal loads and the horizontal loading component are very small, are limited. Okay, because essentially, if you remember, if you have a footing like that, and you have your soil here, and you have an horizontal component, you essentially develop the friction below the footing, then you might have some passive resistance of some remolded soil that you have excavated to pour the concrete of this foundation. So, all in all, the horizontal capacity of this type of foundation is limited. Whereas piles, as we will see, are perfect structure to mobilize the soil resistance, the lateral soil resistance. Now, or if you want, or if you apply uplift forces, upward tension actions, loads, in that case, this is definitely not the right, is not able to provide any uplift resistance unless you apply suction, but this is a different question. This is for offshore foundations. So typically piles, because of their lateral shaft resistance, they can resist also to uplift forces. In marine environment, where wave or flow actions may erode the material from around a foundation, and here you have an important scour effect. The scour effect is when the soil is moved. Here, for example, here you remove this soil, and then this foundation can be under excavated and can no longer provide the resistance. So all these reasons can be better shown in this little scheme, where you have a sequence of different situations which are more or less related to what we have just said. So the case A is when the shallow layer is relatively soft, is not suitable for providing the bearing capacity to a shallow foundations. You have to reach what is represented there as a better, stiffer, stronger soil that can be reached only by deep foundations. Or in the second case is the case there is no stiff, firm layer below. Nevertheless, the foundation, which is developed all along the shaft, is developed not only under the base, but have this mechanism, this lateral mechanism here. Then you are able to reach the capacity you want to reach. So in this case, you see there is also you can possibly neglect or not count on the base, the tip resistance mechanism, because the side shear is prevalent, and this is the case in which you would have a floating pile. Floating pile is something in which you neglect the contribution from the base. Now, the C case is a tension pile, where the applied load is a traction, and the side shear can resist to upward loads. Now, the D case is when your loads, your actions are mainly horizontal, so are perpendicular to the pile axis, and so the interaction mechanism is different from the previous one, when the load is applied actually along the axis of the pile, but you have a strong resistance which is developed by the soil, lateral soil in contact with the pile. And so you can have a set of piles, and you can somehow also build a sort of a retaining structures subjected to horizontal loads. So it's a totally different geotechnical structure, retaining instead of a foundation. Still, you can use piles. So the structural element is the same, but with a different function. And it's important also to remember that piles are typically used in group of piles. You don't build just one single pile. your foundations will be made of different piles or several piles, as well as your retaining structures will be made of adjacent or second piles, one close to the other. The F scheme is what I was mentioning about scour effect. In case of waves, in case of currents, in case of anything along rivers, in offshore, you might have an excavation of the soil around, and in that case you still have your piles resisting to the applied loads. And of course you have always to predict a possible scour of your foundation. This is the case G is not the piles used as retaining walls like the case D. This is still a deep foundation of something which is put on top, but then you excavate at the sides, and then if you have piles, these can be transmitted to the bottom layer, and once again the excavation will not make any harm to your foundation. The final scheme is just in case you have shallow layers with an important volume variations because of different water content variations, seasonal variations. Remember, we already said that this should be put at a depth far or not affected by seasonal water variations, but of course if this means going very deep, then once again piles can be more suitable than shallow foundations. So you have all sorts of reasons why you want to use piles. Typically piles are more expensive than shallow foundations, so the reason is I will spend more for my foundations because I need to. An important question that we have to immediately introduce is that in the case of a shallow foundation, the soil disturbance is limited to a thin layer below the foundation depth. The mass of a soil where significant stress increase occurs or which would be involved in a possible shear failure is practically unaffected by the constructional operations. So how do you typically make a shallow foundations? You excavate your soil, then you prepare the ground for your concrete pouring of your foundations, and then you put your foundations, then you fill the excavation. So the remolded soil, the disturbed soil, will be at the sides. That's why we typically neglect the interaction here with the soil here, and everything basically is dependent on the interaction at the base of the footing. And this will involve all this part of the soil that we have seen in our general shear failure mechanism, or the soil involved by the bulb or pressure for the calculation of settlements. Everything mainly depends on the soil response below the footing, which is typically undisturbed, is not disturbed by the construction of the shallow foundation. So if you run a site investigation analysis, if you want to if you want to build a geotechnical model, you can rely on the soil as it is in order to predict what is the soil response to the application of loads. Bearing capacity and settlement can be predicted from mechanical characteristics of the undisturbed soil, which can be investigated with a suitable site investigation campaign. This is not the case, it's not the same case for pile foundations, because the soil in contact with the lateral pile surface, from which the pile derives its support by side friction, is deeply influenced by the pile installation. Similarly, the soil or the rock beneath the toe, the tip of the pile, is compacted or loosened to an extent they may affect significantly its end-bearing resistance. So you see, in order to install this pile, you inevitably disturb the soil. So the soil around the pile, around the shaft of the pile, or at the bottom, below the tip of your pile, is inevitably affected by the pile installation. And since the pile gets its capacity and its behavior by the interaction with the soil around, this means that we have to consider the soil disturbed, not the undisturbed soil like in the case of the shallow formation. So the obvious conclusion is that the pile behavior is markedly dependent on its installation technique, which, if you put this way, you can think, well, okay, this is obvious. Let's consider the installation technique. But this is, if you think a little bit more, this means that you cannot say, my foundation will be made of, say, 10 piles of a specific diameter, a specific length. You must also say, design the pile installation technique, because the pile installation technique affects the response of each single pile. So in your design, in your geotechnical design, you should not only determine the dimension, the type, the shape, the material, all these things, but also the installation, because the installation technique strongly affects the pile response behavior and its own capacity to the applied loads. So that's why we did not talk about it with shallow foundations, but this is why we will start from analyzing, from describing the possible installation technique. How can I make a pile? How can I find myself with a pile installed like that, and what is the outcome of this interaction? This is why we start from this, which is an important point, because not only the installation technique can affect the pile response, but also how good is your installation technique. Is your installation technique, is it made properly, correctly? Is it getting to the right result? Because you cannot give for granted that this pile will provide some specific, your designed capacity. Okay, so that's why it is important to be on site, on the work site, to check the operations, to check that the installation is made as you have designed. Otherwise, you will have a pile which is somehow bearing less that you have predicted or designed. And this is quite typical to have long disputes if you find out that the pile is not bearing what it designed. Is it a designer mistake? Is a mistake of the workers? Is a mistake of the material? Where is the problem? Because you have many aspects in which you might have differences from what designed. So let's talk about installation. How can you install a pile? How can you also make a pile in your soil? We typically separate. Not techniques, but the way the pile is installed. And we have two categories, the replacement and the displacement. Whereas this term is referred to the soil where you have to install the pile. So replacement means that you remove the soil and in its place you put the pile. So replacement means that you replace the soil with the pile. That you have first to remove the soil, create a hole, and then fill the hole with your pile. Whereas displacement means that you do not remove the soil, you install your pile, and you displace the soil in order to let the pile in. There is no removal of the soil. And immediately you understand that this is quite an important difference, because if you remove the soil, then of course stress will be released, and then you once again you fill the hole. Whereas if you displace the soil, this means that you have to compress the soil around in order to install the pile. The larger the pile, the more you compress the soil. So, and this is the soil which provides you with the shaft resistance. So this is the main difference, okay? This is not yet a pile technology, but a pile technology can belong to one category or to the other, either replacement or displacement. Now, of course, as usually in all classification, you have something in between, you have something intermediate, and you might install your pile with partial displacement, always with reference to the soil. So when we say partial displacement, we refer not to the pile, but to the soil around the pile. Now, virtually, the partial displacement is the best in the sense that provides the least disturbance to the soil. Because if you remove and then you fill the hole, certainly the soil around is disturbed. If you displace the soil, you have to you apply even more disturbance. So virtually, if you want to provide the least disturbance to your in situ soil, you will have to remove partially in order not to displace it too much, but not completely. Now, if you look at the right-hand side of this slide, you have the case in which the replacement can be first require first to bore the soil by percussion or rotary, with or without casing, with or without bentonite. This is a T. Bentonite mud, with or without enlarged base. You might have the continuous flight auger, what are referred as CFA, typically piles, and so on. I will now show you a set of schemes, of pictures, to give you a better idea of what these words mean. But of course, if you have a prefabricated pile, like the old piles, before concrete was somehow invented, a lot of old ancient buildings are founded on timber piles, piles made of wood. So in that case, the pile is prefabricated and must be installed by pushing the pile into the soil and displacing the soil around. So that's why prefabricated piles are necessarily in this category, displacement piles. Now these days, piles are made also, well, typically are made of other materials, not timber, but say steel or concrete, and so you might have prefabricated piles installed as concrete or steel, installed from the top of your ground, still displacing and moving the soil below. But this is not the only way by installing a pile displacing the soil, because you might cast in place your pile, still without first removing. So you typically install a sort of a casing, an empty casing, into the soil, displacing the soil around, and then filling the casing, the hole that you have created, displacing the soil, in situ, not prefabricated. Okay? And these are the type of piles, all these type of piles have been proposed by authors even many years ago, and then different companies have adopted this type of technologies, giving their own name to this type of technology. So this is not a specific technology of a specific company, but is the author who introduced, Raymond West Frankie, they introduced this way of installing a pile. Then different companies use, for example, the Frankie method, and they have called with their own patented name, in the sense that only that company will make the pile in that way. But there are little differences between one company and the other. Now let's see together a few more information on this type of installation. Replacement piles. Installation requires the removal of a cylindrical volume of soil and filling the resulting void with concrete after having installed the reinforcement cage of your reinforced concrete pile. The factors characterizing the installation process are the drilling or the excavation method. There are different methods of producing this borehole in the soil. It can be essentially percussion or rotary drilling, or, as you will see in a picture later on, continuous flight augering is also a form of rotary drilling. Then, when you remove the soil, you have a bore, you have a hole in the soil which can collapse if it is not able to resist with its own shape. So you have to support the walls of your hole before you pour the concrete, before you make your pile. So you might install a casing. In this way you are certain that the soil walls, the lateral walls, will not collapse. Or you can fill this hole with a suitable drilling muds, typically made of bentonite, but it's not the only case. And then the concreting, you first make a hole, then you have to support the hole, and then you have to fill the hole. And you fill the hole by pouring the concrete. If this is a large pile, a long pile, you have to go deeper. You cannot pour the concrete from the top, otherwise you will have the separation of the aggregates. First arrive the coarser gravel particles, then the sand particles inside the concrete. So you have to pour along the pipe, which is called the tremie pipe, and in order to pour from the bottom and then fill the hole with this pipe. I will show you a few schemes and pictures to let you understand better what we refer to. Now, still talking about replacement piles, we said about percussion, the different types of boring. Percussion boring, you see an old equipment, and there are a few also details about the length, the dimension of this percussion boring. This is a bit only by percussion. This is an old method of installation, and this of course depends also on the type of material. If the material can be bored, can be excavated with your specific tool. So, typically pile installation is often thought as a result of your experience. So it's more an art than a science. where experience is relevant. And of course, experience, for all the reasons I'm just describing to you, experience is important. You have to know your tools, you have to know your technology, you have to have experience with the different type of soils. But experience is not the only thing, otherwise you will not need an engineer, which is not very experienced in pile installation. But you have to compare the outcome of your experience on a background of theory. You have to understand what there is behind your experience. So that's why we are now describing all these schemes. Still, the experience helps a lot. Now, this is a more modern equipment, as you see, and this is you have this screw and a rotary boring in which you rotate your tool, and you can see here emerging this casing protecting at least the top of your hole, of your borehole, and then and guiding your tool, this rotary tool. And you see, in this way you can rotate, you can excavate, and you can also at the same time recover the soil from the hole, because the soil will come up along this tool, this auger. And you see, you can this way. This is very flexible. You can make piles up to 3.5 meters of diameter, so very large, enormous piles, and length up to 50 meters, which are about the maximum sizes of your piles. Now, let's try to understand what are the sequences that we have already introduced of our boring. You see, a replacement pile. Okay, so you start with your rotary drive, for example. You typically install something on top of it, even if not a casing for the whole length of your pile. You still put something into the ground in order to position your pile and give some guide in order to go vertically during your excavation. And you see, in this case, you have a bucket here with an opening bottom with a hinge. So you excavate, and then you retrieve your bucket, and then you can empty your bucket and then proceed with the excavation. Now, in this case, you see there is no casing supporting the wall of your pile. In this case, you use slurry. So you fill the hole with this slurry. You see, this is a tank which can provide this slurry. The slurry is a liquid mixture made essentially of water, but also added with bentonite. Bentonite is essentially a clay, a very plastic, very active clay. And so the appearance is like a dirty water, okay, like a mud, a liquid mud. You might add some also other chemicals in order to keep the slurry, this bentonite, floating in circulation and not depositing at the bottom. And this slurry will make a sort of cake all around your sides. And if you keep the level of your slurry in the hole higher than the water level outside. This will also provide a sort of water flow, a seepage of this slurry towards the water table outside, and this seepage forces will provide a support to your walls. Okay? Now, of course, this slurry has to be retrieved once you start pouring the concrete. So, at this stage, you have the hole, which is fully supported by this slurry. Here you see clean the slurry with the descender. The slurry should, if you retrieve sand from the soil, you can using a filter, you can remove the sand from your slurry. Now, essentially, at the end, you have your perfect geometrical, correctly made hole with your design diameter and depth, filled with this slurry supporting the soil. Then you can introduce your cage, the steel cage, according to your design. And even if this is meters of diameter very large and a very deep pile, still you can introduce your cage for all the length of your pile with no restriction. Then you start pouring the concrete. You see in this scheme, this is the green part. This is the tremie type I mentioned before, in which you pour from the top. This goes all along this tube, and this will fill the hole from the bottom. This tremie type has to be always submerged in the concrete in order not to produce any discontinuity in your pile, because the pouring of the fluid concrete will tend to push upwards the slurry. And so the more you pour, the more the hole is filled with the concrete, and then you retrieve the slurry from the top. If you do the operations correctly, then you will have a perfectly continuous concrete piles with inside your steel cage. No matter the dimension, the diameter, no matter the length, you have a perfect pile of the geometry. Now, of course, as I said, all this occurs into the soil. You cannot see. You can monitor, you can check with sensors, with your equipment, but you can't see what's happening. So you must be careful. As a designer, you have to be sure that the pile is made the right way, because otherwise that pile, if there is some soil in between, you have a discontinuity because of the soil which has, for example, has fallen inside the hole. Then you have no longer a pile, a concrete pile. And this can be a serious issue for its capacity. So you have to always check that all the operations are made correctly, and if everything is made correctly, you have your own pile. Where the soil was first removed and then replaced, but at least this is what is closest to your design. If you use the CFA equipment, the continuous flight auger, then you don't need to first remove the soil, protect your excavated soil, and then pour the concrete, because you can do the two things or the three things all together. You excavate with this continuous flight auger. When you get to the final depth, you start retrieving your auger, And from the hollow axis of your equipment, you can pour the concrete. So you pour the concrete exactly with the same tool that you have used to excavate. You go down excavating, and when you come up, you pour the concrete. And this, you understand immediately that this is much quicker in terms of operation, and you don't need slurries to support the sides of the footing. Of course, the cage, the steel cage, is installed only afterwards, at the end, when, of course, the concrete is still fluid, but is also very dense and viscous. So typically it's not possible to install long cages until for the whole length of the pile. And this is why typically with this technique, which is quicker, is better, so it's cheaper, you can reach limited diameter, even if now these days even over 1,000 millimeters, and length up to 25 meters. So we don't have the flexibility and the wide range that we had with the board pile. Now, belonging to the category of replacement piles, you also have micro piles. You might have heard in other activities from in other courses, in other experience, the term micropile. Micropile is not technically correct, but this is the most used term to refer to board pile with small diameter. So the term micropiles is referred to the limit diameter. So we are on the other side on the range of possible diameter, and we are talking of piles which are small like that, okay? 150 to 150 millimeters. So they are particularly suitable in difficult ground conditions or in site with limited or difficult access, for example, for enforcing existing foundations inside buildings. Because of the limited size of the pile, this means also limited size of the installation equipment, and this can go, for example, inside buildings. Now, the problem with this type of piles is that since the diameter is so limited, you can you cannot count on the tip resistance. So these are essentially floating piles. Their resistance is provided by the shaft. But being a limited diameter, also the shaft is of a limited size. And so you have to increment as much as possible the lateral interaction between the soil and the pile. This is why they are made this way. You first drill the hole, you protect the hole with a casing, you install your reinforced cage, and then you tend to pour the concrete not just by gravity, by injecting your concrete mixture, either using compressed air. This is one of the very initial technologies to produce micropiles called palo radice. This was an Italian patent. Now these days you tend to install a sort of a tube where you can install also at important pressures your grout. This will try to go into the soil around, and this will enlarge the nominal diameter of your excavation because you push your grout into the soil, and also will produce not a smooth lateral contact between the pile and the soil, but a very rough contact, a regular contact that will tend to enhance as much as possible this contribution, the shaft contribution. Yeah, this is a scheme of what I was saying. You can use what is called tuba manchette. Tuba manchette is a French term, but means that this is a valved tube. So you have all sorts of holes in this steel tube where you can install your injector, and then you inject your grout from these valves, this manchette. Okay, the final result is a pile, as I said, with a larger diameter corresponding to the nominal diameter of the excavation, and then you have a table where you can see the nominal diameter of the steel, and also the typical allowable load that they can bear. Now, okay, let's have a little break. Before you have your little break, let me first distribute the survey that I have to collect. I know that you have already filled the survey with Professor Marchi, but since there are two modules, two teachers, we have to do two surveys. So you have, I will now give you the survey to fill. You know how it works. You know that you have the first part in which you have to fill the specific the answer to your specific questions, but then there is a back page in which this is free for your comments and your problems that you have had with this course. This is only related to my module, so this is a small part. We have seen each other only a few times, but this is what you have. This is the material you have to use. So let me okay. Now, talking about displacement piles, methods for installing displacement piles are jacking, vibration, and driving. Methods that can be also mixed and use more than one type, one method. The reaction needed to push a pile into the ground is equal to its bearing capacity, which can be very large. This made jacking suitable only for relatively small piles. If you install a prefabricated pile, you have to push inside. You can jack, you can use blows, or you can vibrate. Anything you use to push the pile into the soil somehow must overcome the resistance from the soil. So this is the case if the soil is a good soil with good mechanical properties, that you might have problems in installing your pile. You have to use different technologies. The vibratory driving piles are suitable in loose, saturated sand. Driven piles are commonly used and are driven into the ground by blows from an impact hammer. Now, this is an example of hammers used to install displacement piles, where the difference is how the energy to move the hammer is generated. So compressed air, hydraulic and diesel hammers. Now you see you can use vibration to help your penetration into the soil. This is the case of a pile. You see, in this case, you have to use very long and large equipment, and then you have to install the pile, and in the end you have this picture with all these piles which have been vibrated into the soil. This is the case of prefabricated piles, and the same technology can be used to install sheet piles. Sheet piles are piles which are typically installed one close to the other, providing a sort of walls, sort of what is called a sheet pile walls, exactly for this reason, which can be a temporary structure, can be a permanent structure, then this is depending on your design, but this case of steel sheet piles, with this specific geometry in which one is installed connected to the other. This is what is called a Larsen, due to Larsen, who first introduced this type of geometry, the Larsen type of sheet piles. Well, we are not talking about sheet piles, we're talking about piles, but just to tell you that this is another, with a similar, same technique used also for this type of structure. Now, displacement piles can be, these are very interesting because in principle this can lead you to the best type, the most performing or the best performing pile. These are cast in situ. So they are displacement piles, so without removing the soil initially, installing a casing, and then pouring the concrete and installing the cage inside. So these are not prefabricated piles. So the Frankie type pile is like that. You have a casing, hollow casing, there is no concrete inside, there is a sort of a plug, a concrete plug at the bottom, which is used to install the pile into the ground. So you have this sort of a hammer which drops from a specific height and which falls on top of the plug and will tend to make the casing penetrate into the soil. Once you reach your depth, the depth of your pile, which is of course related to the length of your casing, you then connect the casing to your equipment, to your structure. So you hold the casing, and you give some further drops, further blows of this hammer to the plug in order to expel the plug from the bottom of your casing. Now this looks a bit empirical, looks a bit old, and in fact it has been now made more efficient, a bit more modern, but it still is the potentially the best performing pile. Why? Because you see, when you get when you get to the end and you get in contact with the soil, you then expel your plug, creating a tip, a base of the pile, which is larger than the nominal diameter of the pile. So it's not a cylindrical pile shape in contact with the pile, with the soil, but you have a sort of expanded concrete base. And this, additionally, this is pushed against the soil. creating a perfect contact, somehow a very stiff contact between the pile itself and the soil. If you think, if we go back to our board pile, when you have removed the soil, you typically tend to clean the bottom of your pile, and then you pour just by gravity your concrete. So the contact between the tip of the pile for a board pile and the soil itself in situ is not that good. It's not that perfect. It's not that stiff. Okay? So this means that you will have to develop quite important, large displacement, movement of your pile in order to get the tip of the pile in perfectly good contact with the soil. Whereas in this case, this is already in good contact. Since the beginning, since the construction. Now, you can then install the casing. You have the steel cage. You have the casing outside, so the casing is hollow. You install your steel cage, and then while you remove the casing, you keep pouring the concrete from the top. This means that, but in this case, you can't make this way. You can't make two long piles. Nevertheless, you pour the concrete from the top, and with the hammer you can continue compress the concrete. So you will realize a very good concrete, where the fluid concrete is compressed by the hammer and is pushed outside. So you keep boring, you keep pressing, while you remove the casing, the concrete is going outwards against the soil, thus providing a very rough contact with a lot of little bumps of concrete, once again in perfect contact with the soil, providing a rough and stiff interaction contact also along the shaft. So in the end, if you follow all this operation and you do it properly, once again without allowing the soil to fall inside the pile, because if you remove the casing before you have poured the concrete, then the soil can fall inside and provide discontinuity in the pile. So this and the enhancement of more modern equipments are that you can log all your operations. So you can follow the depth of your pile, you can follow the amount of concrete that you have poured. But of course, the amount of concrete is more than the nominal value, and so you have always to check which is the depth of your casing and the depth of the concrete. Now, these days with the new machine, this is possible. So this is more efficient and this is more reliable. Still, it is very important to have an expert operator able to produce a pile like that. But a pile like that is for a specific diameter, for a specific length, is the best, as I said, the best performing pile. And in a little while we will understand also why the stiffness of the contact between the soil and the pile is so important. Now, a different way of making a cast in situ displacement pile is, for example, by vibrating the casing, not by hammering into the soil. So you have this type of lacquer piles, Raymond piles, which are a bit conical with corrugated casing, and other type of piles, which as I said, has been then developed and patented by different companies. We have not the time and even not the aim of going through all the different technologies which are being developed all the time with improvements and enhancement with respect. We want to understand what are the possibilities in order that when we can analyze one specific technologies which is recommended to us by a specific company, we can understand where it is placed in this overall sketch. Now, the displacement piles, these are somehow screw piles different from the CFA. CFA were mainly replacement piles, even if they do not remove entirely the volume of soil like the bored piles, but CFA were located in the replacement piles. Now here we can have this type of screw piles where the screw is limited to the tip of the tool, of different shape, different size, different distance between the augers. So you have all sorts of possibilities, and at the end of the penetration, the tip is released and the concrete or grout is injected through the hollow stem, while the tool and the stem are withdrawn from the soil. Typical diameters are in the range between 0.3 and 0.6 meter, more or less like the CFA, but this is continuously being developed. Now let's try to understand what are the advantages and disadvantages of different pile types. And this could be longer than just this slide, but it might be useful to understand, to go through this synthetic slide. Displacement piles are suited in cohesionless soils. So let's talk about granular soils, sandy soils. Their installation increases the horizontal stress, the stiffness and the bearing capacity. So if you install a pile without removing, this must displace the soil, will increase the horizontal stress state, and if you have a normal, against the pile, a normal stress which is higher, you get a higher friction. So that's why displacement piles in sand are particularly suitable. They have to be adopted, however, with caution in cohesive soils, because their installation remolds the surrounding soil, inducing high excess of pore pressure. Once again, if we deal with fine-grained material, the installation with no soil removal, so essentially this occurs at constant volume in undrained conditions, this will develop a lot of excess pore pressure around here, and this can reduce the effective stress and reduce the capacity. Now once this excess pore pressure has dissipated after consolidation, you might recover a good bearing capacity. But this means that you have some bearing capacity at the beginning after the installation, which is a bit a minimum of a capacity, and then you have to wait until the end of the consolidation in order to develop full lateral capacity in an undrained, in a cohesive soils. Okay, so typically very recommended in cohesionless soils. Attention in cohesive fine-grained materials. Prefabricated driven piles are limited in diameter and length because, as I said, you have to win the resistance of the soil. You can damage the prefabricated pile during the installation. So they cannot be inserted in soil including cobbles or very dense cemented layers. Additionally, you might have noise and vibration due to driving that can be unacceptable in urban environment, producing noise and damages to the nearby buildings. Replacement piles generally exhibit relatively low resistance in cohesionless soils due to loosening of the soil below the base and surrounding the shaft. The removal of the soil induces a stress relaxation of the soil, so this is a bit the opposite with respect to displacement piles, and then you have a much lower resistance. Range of length and diameter is broad, very flexible, we said that, and the length can be readily varied, and any kind of soils can be drilled. Now, another thing is that if you are not fully certain about the stratigraphy and your geotechnical model, if you have a displacement pile, prefabricated or cast in situ, the length of the pile and the size of the pile is pre-designed. When you have a bore pile, then you can change, during construction, you can change the sizes of your pile. Because you know better the stratigraphy while you excavate the soil. So you can, say, change during the operations the design of your piles. Now, before we go to the proper design, how can we compute the bearing capacity of a pile? We have to introduce another important issue, which is related to the previous one. So we have underlined the importance of pile technology, and because the outcome is never fully certain, because it depends on the technology and how good you have installed your piles, then pile testing is absolutely important. Codes typically require a certain amount of compulsory tests in order to check the quality and the performance of your piles. So once again, this is much more important for piles than for other types of foundations. There is little uncertainty here. Once you have excavated, you know how the foundation you have realized. You might have uncertainties on the response on your geotechnical model, but this would require further site investigation, because this is, as we said, undisturbed soil. In the case of the pile, even if you know the soil initially, then the final outcome depends on what you have done, how you have installed your piles. So before we go, and this will be the final part, to the design of a pile, let's spend some time on pile testing. The purposes of a pile test are to determine the load capacity of a single pile. Well, this is the most obvious thing. This is a full-scale test. I realize a pile, exactly how I think I will install all my set of piles, and then I will tend to load the pile, to measure the settlements, to measure the bearing capacity, and this is a very good, let's say, easy prediction of the pile performance. I am just realizing a full-scale test of a pile performance. Now, it's not always that easy, because piles can reach, you see, for example, 2,000 tons, one single pile. This is an example of large steel piles installed along, I think this is the case of the Tago River, which is close to Lisbon, capital of Portugal, where you have to install all sorts of other piles, where you anchor your beam. In order to apply 2,000 tons, you have to anchor your loads, your jacks, to other tension piles all around it. So just the design and the cost of such installation is quite challenging. So a full test pile to design the pile bearing capacity is not common. Can be required for specific conditions, for specific uncertainties, for specific important projects. Typically, you want just to determine the settlement of a single pile at working loads. So you might not make a special pile for your design and to take it to failure. You just test by loading a pile of your set of piles in order to check that it is good enough and it is in agreement with your predictions, with your design considerations. Okay? If you install, and we will see how you install some sensors, some strain gauges all along the piles, you can then check by measurements, you can separate the contribution of the shaft from the contribution of the tip, which typically from the top you cannot separate. And so you can obtain information on load transfer in skin friction and end bearing. You can just simply verify the pile length because, as I said, everything is inside the soil. You don't know what is the pile length that you have actually realized. And so there are all sorts of tests, non-destructive testing, that will check the structural integrity of the pile, especially the effects of the proposed installation method. For example, if there are discontinuities along the piles. So, moving from top to the bottom, one thing is to do a full-scale testing led up to failure of a pile, which is really expensive and complicated and challenging, especially for large piles, to the non-destructive testing that you can run on a very high number of piles, which are not that precise and that reliable like the load test, but can be more widely carried out. So let's now have a little look at all these type of tests. This is the arrangement of a vertical load test procedure. You see the center pile is the pile tested. Then you have a reaction beam. You have an hydraulic ram or jack able to push the pile. And of course the reaction beam must be anchored on a set of reaction piles that will provide reaction exactly in the same way by developing the shaft resistance in the opposite direction. So the reaction to the jack can be provided by a cantlage or a bioreaction beam. A load cell measures the applied loading and dial gauges measure the settlement of the head. You can apply a load and measure the settlement until settlements die out, or you can apply a constant penetration rate test in which you just measure, of course you must go very slow, and you develop, you measure the settlement corresponding to a specific load which is increased at constant rate. Typically the most common procedure is the A, maintained load test, where the load is increased in definite steps and is sustained at each level of loading until all settlement has either stopped or does not exceed a specific amount in a certain given period of time. Now, this is a possible response of a full-scale test on a pile, and we will, of course, understand better and come back to the trend of this curve. But it is already very useful to spend a couple of words on this shape, because you see, you have the load settlement. This is the standard way of providing results of a pile loading test. So you have the load, they are typically referred as P delta, which is the load and the settlement of the pile. So this is not designed, this is not given, provided by calculations, this is just measured. So you increase the load and you measure the settlement. And you see that you have two curves of two different piles. From the textbook I mentioned at the beginning, these are typical results of a pile load test. But you see the shape of the curve is really different. If you think at the slope of this curve, the ratio between load and settlement, the tangent, the slope of this curve, is somehow related to the stiffness of what? Of the pile response. Okay? So the more steep is the tangent, the stiffer is the response. But so what is stiff? Is the interaction mechanism which is stiff. So you see, for example, in the second curve, you have a curve which is much steeper, which means that you have a stronger reaction, a strong development of capacity at a relatively small settlement. It is true that also the scale is different in millimeters, but anyway, you might have a curve which is steeper, meaning that you apply the load and you immediately develop some capacity. And this is essentially due to the shaft mechanism. Because remember, we refer to two separate mechanisms, one along the shaft, one at the base, providing capacity. But the two mechanisms come into action at different amounts of settlements. Whereas the shaft capacity mechanism comes into action immediately. Immediately, not in terms of time, in terms of settlements. So the sooner you apply the load, the sooner you develop, even at small relative movements between the pile and the soil, they will develop the reaction, they will develop the capacity. Whereas this is something similar to the shallow foundation, in which the pile must to go down, develop slip surfaces, tend to punch the soil, and so this mechanism, which can provide some important contribution to the capacity of the pile, requires large settlement. Typically, it is reckoned that you have to develop, you have to go down about 20% of the diameter. So consider that you have a pile of 1 meter diameter, 10% means 10 centimeters or 20 centimeters. So in order to develop the capacity at the base, you have to go down 10 or 20 centimeters, which is a lot, because this means 10, 20 centimeters of settlement of the pile. And piles, we said at the beginning, are typically used to reduce settlements and differential settlements. So we cannot allow such a large settlement to the pile. And this means that we cannot rely on the bearing capacity contribution if we want to reduce settlements. Now, two things. We can rely on the shaft capacity contribution, which are developed for a much smaller settlements of the order of millimeters, not centimeters, millimeters. Or we have to improve the contact at the base, and or we must improve the contact at the base in order to have, as we said before, a much stiffer contact between the pile and the soil, like in the Frankie pile, for example, or the prefabricated piles. So the displacement piles do behave much better than board piles from this point of view. Now we will come back to this, because in our design calculation we will have to take into account which is the pile technology, what is the stiffness of the interaction mechanism, in a somehow empirical way, using coefficients, using tables, but in our design we have to consider this. And everything is related to the stiffness of the mechanism. So, for example, if we go back to this curve, we see that the first pile will be a pile which develops more or less always first the shaft resistance, then the base, but they are developed all together. And you need up to 10, 15 millimeters settlements to develop the high capacity. And this capacity tends to increase with the settlements. So you never get a real limit, a real final value. Whereas in this case, you first develop almost the full capacity, and then you go down up to 70, 80 millimeters, because typically this is the case of a floating pile, in which you have no contribution from the base, and once you have reached the full capacity, developed along the shaft, then the pile will tend to go down at constant load. Okay, so these two curves are both possible, but tell us of a different response, of a different behavior of your pile. And this is another reason why a full-scale pile test is very useful, to understand also what is the distribution of the two contribution of the two mechanisms. Now, non-destructive testing tells us almost nothing about the capacity of the pile. They are quality testing. They tell us about the quality of the pile. So we want to see if the pile was installed with the diameter designed, with the length designed. So we want to check is a quality check at the end of the installation. And these types of integrity tests can be acoustic, radiometric, seismic, stress wave. All these are relatively simple. For example, in the case of acoustic test, you have to anticipate and install, before pouring the concrete, you have to position a hollow tube inside the pile. You can see it in the transversal circular section of your pile. You have previously installed 1, 2, 3 hollow tubes. In one tube you can install a transmitter, something transmitting acoustic waves, and in the other tube you install a receiver. So you know exactly the geometry of this triangle, you know the distance between the two tubes, and you measure the velocity of your waves through a specific material, which is supposed to be good quality concrete, homogeneous concrete. If, for example, during the pile construction, something wrong happened and the soil collapsed into the pile, into your hole, and so you have no longer a full cylindrical homogeneous concrete pile, but you have something which is also there is some soil or other material, then the velocity of the propagation of the wave will be different from what you know is the propagation rate in the concrete. And for example, you can see here, this is a graph telling you the time in microseconds from the transmitter to the receiver. Of course, the longer the time, the smaller the rate, the velocity of propagation. And you see clearly, it's not always that clear, but this is this is a possible result, a real result, in which you can see that there is some specific depth, you can see that the time is much larger, it's much bigger. This means that the propagation rate is reduced, and this is because something wrong occurred at that depth. This is not the propagation rate through homogeneous concrete. And this means that at that depth you have a serious problem. Now what can you do? Well, the pile is done, the work site is over, there is little you can do, but of course at least you are aware, you know, you will probably excavate, you will check other piles, you will probably remake a new pile, because this pile is not was not installed according to regulations and agreements and so on. So this type of integrity test can be carried out on a large number of piles of your set of piles, and so is a good check of the quality of your piles. Of course, the best way is also to be on site and check what some engineer should always put an eye on the work site. Now you see, this is the possibility of instrumenting along the length of the pile, including some strain gauges along the strain gauge, along the steel cage. In this way, you have a sort of this graph. You see, this is a graph in which you have the load measured by each single sensor, each single strain gauge, along the depth, increasing the load on top of the pile. And you see that the pile, the load, is not constant along the pile, because the pile is not suspended, not that you apply the load and you get a reaction here. You have a reaction all along the shaft of your pile, so that you apply a load here, and what you get at the bottom is only a fraction of what you have applied on top, because most of the pile load has been transmitted to the soil through the shaft mechanism. So that's why you have a higher load near the surface, and then you reduce the load, and only a small part, in principle also, if you have a floating pile, no load gets to the end, and so there is no contribution from the base capacity. Now, how do you know when you apply the load what is the reaction, what is the mechanism, how the load is transmitted along the depth to the soil? Well, the only way is to put these sensors along the cage, along the depth of your pile, the length of your pile. And this can be done, but on specific pre-arranged piles. And then you have to apply the load on top in order to measure the different sensors. So, once again, this is not like the integrity test that we have seen before, but this is a very useful and important information. Now, we have to consider that piles are rarely used as single pile. They are usually in groups and are connected with a cap at their top. Only in the last few years the existence of large diameter piles has sometimes modified this practice. Actually, for example, for offshore structures, wind farms, for example, wind turbines, they are founded on a single enormous diameter pile, let's say 8-10 meters diameter steel pile, which is called monopiles. But this is a very specific application. This is just to let you know that the things we say are not always valid for all structures. Standard group piles are in group, and you have to calculate, you have to design the response of the group of piles. But you start from the design of a single pile. So you evaluate the single pile behavior under an actual load. Then we know that the load can be also perpendicular to the axis, but we will limit to the prediction, to the design of the capacity of a single pile. Then you have to consider that the capacity is made of a group of piles. Well, you can say, okay, if I calculate the capacity of a single pile, I have 100 piles, and so my overall capacity will be 100 times the capacity of a single pile. Well, this is not always the case. The capacity of a group of piles can be limited, can be less than the sum of each single pile capacity because of a group effect, because they interact each other. But sometimes can be even higher because the installation of many piles, one close to the other, can increase the capacity of the single pile. So there is an important step after the evaluation of the single pile behavior in order to get to the response of a pile group, both in terms of capacity and in terms of settlements of the pile group. Now, once again, at the level of this course, we will deal only with the capacity of a single pile, actually loaded along its axis. But if you want to design a real structure, you need to consider a group of piles. And once again, this will be dealt with in your next year course, Design of Foundations and Retaining Structures, in which the single pile capacity will only be kept, and then we will go on discussing about group of piles, piles loaded laterally, retaining structures, and all other things that I have shown you today. Now, I think this is time to start introducing the design of the capacity, not the settlements. We will limit ourselves to the capacity of a single pile actually loaded, which corresponds to this situation. I will just give you a couple of comments on this slide, and we will start on this point next Tuesday. But this is the scheme where we start from. So we have a pile length of a specific diameter, cylindrical shape, very simple. You have a capacity along the shaft, which for unit area can be referred as small s. Small s is the unit shaft capacity, then which must be multiplied by the area of the shaft. And then you have another unit bearing contribution, which is small p, times the area of the base. You have capital P. Okay, so you have your Q load applied to the pile head will be distributed along a P, normal pressure at pile base, and S, which is a unit shear stress at the lateral interface. Now, all our efforts, design efforts, go into the prediction, into the calculation of these two contributions, P and S. But the calculation of P and S must take into account all the aspects we have introduced today. File technology, for example, is one important issue. The simple vertical equilibrium requires that the applied load is given by the area of the base times P plus the area times S, and then you have to consider also the weight of the pile, which is not explicited here but must be considered because the capacity must also support the pile of the weight of the pile. Now look that along the shaft you might have different soil conditions, so different values of S, because you might have a stratified soil, and so this is not just a simple multiplication, but this is an integral of S along the length of your pile, from 0 to L. Okay, let's stop here for today, but of course this is just it's not the end of this topic, but this will be completed next Tuesday. So see you next time.